Welcome to Lesson 16, Stress, Strain and Young's Modulus. Here's the plan for today. When you pull on a material, one of two things happens. If the deformation is elastic, it returns to its original shape once you remove the force, like a rubber band snapping back. But push it too far, past a point called the elastic limit, and the deformation becomes plastic. It's permanently changed and it will never go back to how it started. The formal words for pulling and pushing are tension and compression. Pulling a material apart applies a tensile force, and pushing a material in applies a compressive force. In this topic, we almost always test materials as wires under tension, because a long, thin wire stretches by an amount that we can actually measure. Now, why did we invent stress and strain when we already have force and extension? Because force and extension depend on the shape of the sample. A thick wire needs more force than a thin one made of the same material, and a long wire stretches more than a short one. That tells you about the sample, however, not the material. So what we want to do is standardise this. Stress is the force divided by the cross-sectional area. That removes the thickness. It's measured in pascals, the same as pressure. And strain is the extension divided by the original length. That removes the length aspect. So strain is a ratio of two lengths, so it has no units at all. Now we can compare steel to copper fairly, regardless of the shape of the sample we happen to test. Young's modulus is simply stress divided by strain, and it's the material's stiffness, independent of its shape. Substituting the definition gives E equals FL over A delta L. A quick sanity check for your calculations. Young's modulus values are typically in gigapascals. That's around 10 to the 9. So if you get an answer around 10 to the 11 for steel, that's entirely reasonable. If you get something like 50, however, you've probably dropped a power somewhere. Expect big numbers. Here is the graph that tells a material's whole story. Be careful with your axes. Stress goes on the y-axis, strain on the x. 1 is the linear region. 2 is the limit of proportionality. 3 is the elastic limit. 4 is the yield point. 5 is the plastic region. And 6 is fracture. At first the line is straight. Stress is proportional to strain, and the gradient of that straight part is just the Young's modulus. That linear behaviour ends at the limit of proportionality. Just beyond it lies the elastic limit, the last point from which the material will still spring back. Past that, you're into permanent deformation. The yield point is when the material suddenly gives and stretches a lot for a very little extra stress. Then comes the plastic region, and finally fracture, when the material breaks. And the shape of that curve tells you what kind of material you have. A ductile material has a long plastic region. It stretches and deforms a lot before it breaks, which is exactly why you can draw it out into wires. A brittle material has almost no plastic region. It goes up the elastic line and then just snaps. Think of the difference between bending a copper wire and snapping a piece of chalk. One more note. A wire stretches far, far less than a rubber band or a spring, so don't expect the same scale of extension. Make sure you understand all the points on this graph, as any of them could come up in an exam. As with springs, the energy is the area under the curve. But here's the interesting complication. Once a material has gone plastic, the loading and unloading curves follow different paths. Rubber is the classic example. Stretch and release a rubber band, and the two curves enclose a loop. That's called a hysteresis loop. The area of that loop is energy that didn't come back out as useful elastic energy. It was lost as heat. And this is a genuinely observable effect. Stretch a rubber band rapidly a few times and you can feel it getting warm. That warmth is the hysteresis loop. That's the end of the video. Thanks for watching, and check out my tutoring page below.